This is the second part of a two-part series looking at density, pressure and upthrust, and the focus in this video is to consider upthrust, and we're going to have a little look at some of the thinking that Archimedes did many years ago. So the diagram that you're having a look at then is an object which has been fully submerged in a liquid of density rho, and because it's been submerged, it's under pressure. Now the key thing here is that the pressure is different at the top face and the lower face of the object. And the reason is the top face of that object is at a depth of h1 below the surface, and the lower face is at a greater depth, h2. And so what that means is that there is a greater pressure here compared to here, and I'm denoting that with the length of the two arrows. And so therefore there's a greater force acting on the base of the object compared to acting at the top of the object. In other words, there's a resultant force, and the resultant force is acting upwards, and this is what we mean by upthrust. Okay, it's the resultant of the two forces, and it's going to be in that direction. So on the left, you've got a derivation. It's the resultant force that we want. So if we rearrange the pressure equation, force is pressure multiplied by area, and pressure is rho GH. So we can calculate the force by multiplying those four things together. And so we've got a force on the upper surface, which is rho GH1A, and we've got a greater force on the lower surface, rho GH2A, and therefore the resultant of those is basically the difference between them, isn't it? So if we pull out rho G and A as common to both, then it's the bigger minus the smaller of the two forces, H2 minus H1. And that is what we mean by upthrust. It's that resultant force that acts due to the difference in pressure between the upper and lower surface of that object. However, we notice perhaps that we've got area times H2 minus H1. Sorry, just letting my brain catch up with my mouth. So that is effectively the volume of that object, isn't it? Because H2 minus H1 is effectively that dimension of that object. So if we multiply the area, A, of the object by that change in height there, that's going to give us the volume of the object. So in other words, upthrust is rho GV. Okay, now you're going to have to be very careful along the way here with all of our notations. V here is the volume of the object, isn't it? But actually, if that object is fully submerged, the volume of the object and the volume of the fluid that we displace is exactly the same. All right, so this V here can mean either the volume of the object or the volume of the fluid that's displaced, as long as that object is fully submerged. So another thing to notice then is we've got density and volume being multiplied together. And if you rearrange your density mass volume equation, density multiplied by volume is of course mass. So upthrust becomes mass times G. Mass times G is weight. So we have this nice little relationship here that upthrust is equal to the weight of the fluid that we are displacing. Okay, now again, we need to be very careful here. We're not talking about the weight of the object. We're talking about the weight of the fluids that we push out of the way and that we displace because we have submerged that object. And this is the basis of Archimedes' principle. Archimedes was a brilliant mathematician. I think he came up with one of the earliest algorithms for working out pi a couple of thousand years ago. He's the guy in the bathtub who has that eureka moment. If you know your kind of your stories, he was tasked from memory with working with the king at the time to figure out whether some gold was fake or not fake. And he works this out while having a bath, because he gets in the bath, he displaces a load of water, has a eureka moment, and there is the story. And you've got a little YouTube clip if you really want to find out a bit more about that story. So Archimedes' principle states that when a body is submerged into a fluid, there is an upthrust acting on it, which is equal to the weight of the fluid that is displaced. So this little animation here, there's quite a few things going on here. So you may have noticed that balance changed position when that object was placed in it. So the weight of what was on the right-hand side increased, and we are displacing a certain volume of water. Now, because that object is fully submerged, we would expect the volume of that water that overflows into that beaker to be exactly the same as the volume of that object that is being submerged. Okay, so as that object gets let go, it displaces more and more weight of fluid until the weight of the fluid that it displaces equals the weight of that object. So if that object is a 10 Newton sphere, it displaces 10 newtons of fluid. Okay. Now, let's take this idea one stage further then and apply this kind of principle that Archimedes came up with and kind of relate it to density. So you've got two things happening in this diagram. You've got fully submerged object. There is the weight of it acting downwards, and you've got upthrust acting upwards. Okay, and the reason we've got upthrust, just to remind you, is that we've got displaced liquid. We've got a difference of pressure between the top and the base of that object, and that's giving rise to that upthrust. Okay, now the question as to whether that object is going to float or sink or remain kind of hovering is all dependent on the magnitude of U and W. Okay, so let's work out upthrust and weight of object then. So upthrust is the weight of the water that we displace. So we've already got that on this screen. So that is equal to the mass of the liquid or the fluid that we displace multiplied by G. And mass is density times volume, isn't it? So it's the density of the fluid multiplied by the volume multiplied by G. Okay, so that's our expression for upthrust. Now, the weight of the object, that is equal to the mass of the object multiplied by G. Mass is density times volume, so it's the density of the object multiplied by the volume of the object multiplied by G. Okay, now the reason that I've not distinguished for volume is because the volume of the object and the volume of the fluid are identical if it's fully submerged. So the two V's in our two expressions here are exactly the same. So there's my expression for W and there's my expression for weight. Whether an object floats or sinks then is all dependent on density. Okay, why am I saying that? Because if an object is floating, okay, then presumably upthrust and weight are equal to each other. In other words, rho F V G is rho object VG. Okay, and so G's cancelling out. The volumes of the objects are the same. Okay, and that's telling you then that those two densities are identical to each other. So if you can get an object to fully submerge and then hover and remain stationary, that is telling you that the upthrust and the weight are equal to each other, and that's telling you that the density of the object and the density of the liquid or the fluid that it is in, they are equal to each other. Okay, but what about the other two examples then? What about the example of an object that floats up to the surface and remains on the surface? And what about the example of an object that sinks and falls to the base? Let's have a look at those two and how Archimedes helps us with that. Okay, so let's imagine that the object that we're about to drop onto the surface of that fluid has a weight of 10 newtons. Okay, and there is the fluid. Now, if that object is going to float on the top, then presumably the density of the fluid is less than the density of the object. Okay, so an example of this would be something like a polystyrene sphere and water. You would expect that polystyrene sphere to float on the top of the water because it has a lower density than the water. Sorry, I've got that wrong. Let's just change that to a greater than sign. Okay, the density of the fluid is greater than the density of the object. So what that means is that as we lower that object into that water, that object is going to displace its own weight. In other words, we are going to displace 10 newtons of water. However, because the density of that water is greater than the object, the volume of what we displace is going to be less than the volume of the object. So we might displace the bit that I've shaded in purple. We might displace that volume of fluids, that volume of water. And so when that object comes to rest, okay, it's going to be partly submerged under the water. Okay, there is going to be a volume that remains above, and there is going to be a volume that remains below. Okay, but the key thing is that we are displacing the same weight of water as the weight of the object. Okay, so if the object has a weight of 10 newtons, we are displacing 10 newtons of water, but because the water is more dense, that means 10 newtons of water has a smaller volume than the volume of the object. Okay, what about the final situation then where an object is sinking? Well, that's telling us, I think, that the weight is greater than the upthrust, I think is what that's telling us. So in this situation then, the density of the object is now what is greater. Okay, so an example of that would be a piece of metal and dropping a solid lump of metal into water. Okay. So because it sinks all the way to the bottom, the argument is around volume. Okay, whatever the volume of the object is, the volume of the fluid that we displace is equal. However, because the object has a greater density, then the weight of what we displace is less than the weight of the object. Okay, so in other words, the weight of the fluid that we displace is less than the weight of the object. So if the object is a piece of steel and it's 1,000 kilograms, when we displace that volume associated with that object, it might only represent 1 kilogram of water. Okay, so therefore the weight is greater than the upthrust, and therefore that object sinks. Okay, so that's quite a difficult set of ideas. So you're going to need to go back over that PowerPoint again and just get real clarity on the arguments being used in those three situations. Okay, so situation one was when an object is fully submerged but reaches equilibrium. Okay, so it is floating but completely submerged. Situation two was an object that was only partly submerged, so still floating but only partly submerged. And situation number three was an object that sinks to the bottom of a container. So there's kind of a classic example then, isn't there, around kind of like the iceberg. We even have this saying, don't we? It's just the tip of the iceberg. In other words, there's a lot more that you can't see compared to what you can see. Okay, so let's have a little look at this question here, which asks us what fraction of the ice is above compared to below the water. Okay. So because that ice is floating, okay, and it's partly submerged, the amount of upthrust and weight are equal to each other. Okay, so in other words, the weight of the ice is equal to upthrust. And Archimedes says that upthrust is equal to the weight of the water that we displace. Okay, so let's calculate both of these two things then. The weight of the ice is its mass multiplied by g, and the weight of the water that we displace is its mass multiplied by g. Mass is density multiplied by volume. So the mass of the water is its density multiplied by its volume multiplied by g. And the mass of the ice is its density multiplied by its volume multiplied by g. So we can get rid of the g's. Now in this situation, it's important that I distinguish between my two volumes because now they're different. So earlier when we looked at a fully submerged object, because it was fully submerged, the volume of the object and the volume of the fluid that we displaced were the same. But this object isn't fully submerged. Okay, so the volume of the ice is the whole of the iceberg, but the volume of the water that we displace is just the bit that is underneath. So if I rearrange this, I can work out the volume of the water to be the density of ice divided by the density of water multiplied by the volume of ice. The question gives me my density values. So the density of ice is 890, the density of water is 1030. And if I calculate that fraction, it comes to 0.86. Okay, so in other words, the volume of the water which gets displaced is 0.86 times the volume of the total amount of ice that we've got. Okay, so if I draw this, there's the water, there's the iceberg above, there's the iceberg below. Okay, in purple, that is the volume of water that I displace. Okay, that is equal to the bit of ice that's underneath the water. The total amount of ice is all of that, the bit that is both above and also below. Okay, so if I just color code those to link into what I've just highlighted there for you. So in other words, as a percentage then, the volume of water that gets displaced is 86% of the total volume of the ice. So in other words, 86% of the ice sits under the water and the remaining 14% is above the water. Okay. So here is a more kind of broken down question that you might want to have a little go at. So do it in numerical order, and you should work out in this instance what volume of the apple now is below and above the water. Okay, so you're going to do exactly the same kind of thinking as we did for the iceberg for this example here. Okay, so in my experience, this is a concept that students tend to find quite tricky, and it's going to require a little bit of going back over this video and this presentation. Okay, and obviously when I return, if you've got any questions that you want me to have a look at this, then obviously we can focus some time around that.